So this is where it starts getting interesting in this class. Not that it hasn't been interesting up until this point, but a lot of math is learning how to do something and then learning how to undo it. And we've kind of talked about antiderivatives and stuff like that a little bit. But this is where we really start getting into the whole idea of how the branches of calculus are connected. So far we've been dealing with rates of change. We've been dealing with derivatives, and that's a branch called differential calculus. We're now ready to figure out if we've got a function and it's a rate of change, it's going to accumulate whatever it's measuring. Okay, and that branch of calculus is called integral calculus. So we've been working with differential calculus. We're going to do a little bit of, working with differential calculus. We're going to do a little bit of integral calculus and try kind of understand how those two branches of calculus relate to each other. And then in 1220, you do a lot of integral calculus. So this section is on areas and distances for the most part, and we're going to talk a lot about how to find areas. And that sounds like kind of a silly topic, but we're going to start off with that example that I gave last time. Hopefully you did that. If you didn't, it's a fairly easy thing to understand, especially if you follow the instructions, right, Ben?
Yeah.
Okay. All right. So I gave you a piece of graph paper that's half-inch grid paper. So if you put your hand on there, definitely put your fingers together, put it on there, and then trace the outline of your hand, and then just connect the two sides of your wrist. Okay? Now, your hand is a very funny looking shape. In fact, mine's really funny because if you look at my fingers, much like Weston, there's gaps in between them. There's some hereditary condition. My fingers don't touch. Okay? So if you trace the outline there, that is a really difficult thing to say. I know exactly what the area of that shape is. Well, one way that I could guesstimate what it is slap that on a piece of grid paper and then go through and count. Now, if you count the stuff that's entirely inside, and these little squares are relatively large, but still, if I go through and I count there are 81 squares that are entirely 100% inside my hand. So that would be a bit of an under approximation. I'm leaving out all the things that are on the border or even touching the border, okay? So if I have 83 half square inches, okay, every 4 of those would make 1 square inch. So if I divide that by 4, if I take 83 and divide that by 4, I get 20.75. So about 21 square inches right here, okay, as an estimate, assuming the graph paper is accurate and stuff like that. But that's going to be a little bit on the low side. Well, the other thing that we could do is we could count anything that even touches the border, anything on the inside and anything that touches the border. So I went through and I counted how many border squares there were, and there were 51 of them. So if I add the two of those together, I end up with, what is that, 134? And if I divide that by 4, let's see, that would go in there 30 times, is that right? Yep, 33 times. Approximately 33 square inches. So there's a big discrepancy there. Pretty big discrepancy. Okay? Now, this is an overestimate for the area of my hand, and this is an underestimate for the area of my hand. So it's probably somewhere between there. So how could we make a better estimate than having what's definitely an underestimate here and what's definitely an overestimate there? Average the two. Come up with something in between there. So we could add the two of those together, average the two of them, so that'd be what, 53-ish? So maybe 26 square inches or so. Okay, that seems pretty big for my hand there. Maybe the graph paper was off just a little bit. Okay, but that would be one way to estimate. Okay, now that makes the counting relatively easy, but there are other ways where we could get much more accurate answers. Okay? Can anybody think of a way where we could get a more accurate answer than using this type of graph paper?
You could get one with smaller squares.
Yeah, smaller squares. We could do a 1/4 inch or an 1/8 inch or even a 1/10 of an inch. Little tiny squares. Okay, and let me show you what that would do for you. Okay, I actually drew these in right here. So let's say that I used 1/4 inch graph paper. So this is 1 square inch. These 4 is 1 square inch. Okay, if I did 1/4 inch graph paper, here's what would happen if I were making that decision about is it entirely inside or is it on the border on that one. So let's take a look at this, this square right here. I counted it on the border, and only this tiny little piece right here actually has any area of my hand. But if I used smaller squares, if I used 1/4-inch squares, I'd only count this little one, and I'd get rid of all of this excess right here, all of this overestimate right here, okay? On this one right here, same type of thing. I'd only count these 2 squares rather than all of that, so it cuts down on my error. And we could get really ridiculous, and we could use little teeny tiny ones like this. And maybe I'd only count this one out of those 16 squares that I used to count as one single square, okay? So if I use smaller squares, if I use a smaller grid, I'm going to get a more accurate answer. Now, if it's going to be more accurate, what's my trade-off for that? What if I did use 16th-inch grid paper? That would take you forever to count, wouldn't it? I mean, it takes long enough to count these. Imagine if every one of those was broken into tiny little chunks there. Lots and lots of counting, but more accurate, okay? So if we make that little mesh a little smaller, we get a more accurate answer, but it's harder to actually come up with it because you have to do so much counting. It's tedious at that point. Not that this wasn't tedious, okay? Make sense? This idea that you can get a more accurate answer for an estimate on area by taking these tiny little slices, these little tiny little rectangles, these tiny little squares, is a really important idea, and it's a really valuable tool that we're going to use in just a second. Any questions about that? Okay, let's come back here and let's take a look at this now. And it says, what can we do to improve the accuracy of our estimate? Smaller squares. More to count, but they'd be more accurate because making that decision about whether or not it's inside or outside, there wouldn't be as many as that we'd have to make that decision on, okay? Now, we're going to switch gears just a little bit, and we're going to deal with, so this section is on areas and distances. So we're going to talk about a distance here for just a second, and then we're going to come up with how it's related to a distance. So it says, suppose we traveled for 5 hours at 60 miles per hour. What distance would we travel in those 5 hours? Piece of cake, right? It's going to be 300 miles. And we simply use distance equals rate times time. So if we know the rate is 60 miles per hour and the time is 5 hours, we just multiply the two of them, we come up with 300. What about between hours 3 and hour 5? How much distance would I have covered? 120. How do we do that?
2 hours.
Same thing, okay? We're just using a smaller length of time, but we were still going 60 miles per hour. So it's just the 2 times 60. We end up with 120, okay? So this thing right here, this velocity right here, or this information about 60 miles per hour, it tells us how fast we're going. The entire time we were going 60 miles per hour. So if we thought of that as a function, as a velocity function, it's a constant. We're always going 60 miles per hour. So the velocity, which measures rate of change of position, has accumulated a change in position. We hadn't gone anywhere when we started, but by the time we're done with those hours going by at 60 miles per hour, we've accumulated 300 miles in position change. We're now 300 miles from wherever we started, okay? So, in addition to solving this problem this very simple way, using this formula that you've known for years, we can actually solve it using a graph. And in the long run, this is going to be much more helpful and is going to kind of help us bridge the idea of going from areas to figuring out distances. Because that distance is a piece of cake to figure out here. We're going to use that very simple problem to figure out something that's a little bit more complicated. So we're going to look at this graph right here. And notice that I've got this labeled as v of t, which makes this a velocity graph. Now, I'm a big fan of labeling the type of graph you have because in calculus, we learned how to go from position to velocity to acceleration by differentiating. We also learned how to go from acceleration to velocity back to position by anti-differentiating. And that's really what we're talking about here. We're going to kind of formalize this process over this entire chapter. So this is a velocity graph, and let's take a good look at this velocity graph. We were going 60 miles per hour, okay? So this vertical axis is the velocity in miles per hour. This horizontal axis is the time in hours, okay? So if I looked at this rectangle right here from 0 over to 5 hours, how tall is this rectangle? Okay, so I'm looking at this rectangle right here. That rectangle is 60 tall. What are the units? Miles per hour, right? Because that's the unit it has right there. How wide is the rectangle? 5, and the units would be hours. So if I found the area of that rectangle, the area of that rectangle would be the simple calculation base times height, or you could do height times base, it wouldn't make any difference. Okay, so I'm going to do 60 miles per hour. That's the height, and I'm going to multiply it by how wide it is. That's 5 hours. So I can cancel the hours, and I end up with 60 miles times 5, so I end up with 300 miles. So the area of this little rectangle right here is 300 miles. The exact same answer is if I just took the distance equals the rate times the time. That distance can be produced by taking the height of this rectangle and multiplying it by the width of the rectangle. 60 miles per hour tall, 5 miles wide. Multiply those together, the units cancel, so I end up with 300 miles. Does that make sense? It's a little different, but it comes up with the same answer. Okay, and geometrically that makes sense, right? Okay, so the area between the velocity curve, and I'm going to call this a velocity curve, and the horizontal axis is the position change. If I've got velocity, and I find the area between the velocity curve and the horizontal axis, that's going to tell me how much position change occurred. In other words, it's the net change in position, or we call that the displacement. And we talked about displacement, I think, in chapter 3. Okay, so the cool part about this is I don't have to use this entire rectangle. Okay, I used this portion from 0 to 5 to figure out the answer to that first question. What if we said from hour 3 to hour 5? Well, the rectangle wouldn't start right here, it would start right here. So the area underneath this velocity curve and the horizontal axis would start right here. So kind of put a wall up right there and stop right here, put a wall up right there. And it's this nice geometric shape, this nice rectangle. How tall is the rectangle? 60 miles per hour tall. How wide is it? 2 hours. So 60 miles per hour times the 2 hours to find the area there. And this area right there would be 60 miles. So the area underneath this velocity curve actually represents a distance. And that's kind of the relationship that we're heading toward, although we're going to make this much more broad by the time we get done with this chapter. Okay, are there any questions there? It wouldn't be miles squared, no, because this is just, so this is 60 miles per hour tall. That's literally how tall that is. And this is 2 hours wide. And when I take the base and multiply it by the height, just the hours would cancel. Nope, so not square miles. Good question. Anything else? Okay, so that is a very simple shape, a very simple function, a constant function, a very simple shape, a rectangle. But usually things don't turn out that easy. So what if we had a function that was like this? What if we changed our velocity function? Okay, what if it wasn't a constant? Okay, could we do the same type of thing to figure out how much distance we'd covered? So here's the function that we're going to use now. Our velocity function is t squared. So if you plug in 0 hours, our velocity is 0 miles per hour. If you plug in 2, square that, we end up with 4 miles per hour. So the longer we're going, the faster we go. We start out really slow, and then we just go faster and faster and faster and faster. So here's our velocity curve right here. Okay? And let's say we did that for 3 hours. Well, using the same analogy, if this is a velocity curve, just like this is a velocity curve, I should be able to figure out how much distance I've covered in that time by figuring out the area between this curve and the horizontal axis. Now, it said we're going to do this for 3 hours, so I'm going to drop this line straight down right here, kind of put that wall up there. And we want to figure out what is this area right here. So what would this be if I were to shade this area in right here? So again, it's a good idea to think about what type of graph is this. This is a velocity graph. And then the real question is, if that's a velocity graph, and I found the distance that I traveled by figuring out the area underneath this curve, really easy geometric shape, how would I figure out the area underneath this curve when it's a much more complex geometric shape? Break it up into simple shapes. Juan is exactly right. We're going to break it up into simple shapes. Okay? So let's write that down. Break into simple shapes. Now, what would be the most simple shape we could do there? We could do a triangle. That would be great. That would be okay. We could do one big triangle. Okay, but we've got a lot of error right here. Okay, a lot of overestimate. Okay, we're going to stick with simple shapes like rectangles. Rectangles are very easy shapes to work with. Okay, rectangles are similar to those little squares that we were using to estimate the area of our hand. So we can apply some similar principles. Okay, so the thing that made that first example very easy is we had a nice geometric shape. If you've got a nice geometric shape like a rectangle, a triangle, a circle, or a trapezoid, you might want to think about trapezoid, we'll come back to that in a second, okay? Then finding the area between the curve and the horizontal axis is going to be relatively simple, okay? Well, this has a curved top to it, and it's not a circle. So it's not exactly a rectangle, not exactly a triangle, not exactly a trapezoid, okay? So we've got to be a little bit clever about how we do this. So here's how we're going to do this. There are lots of different approaches. They all come down to basically this idea, okay? So this entire section is about what's in this box right here, okay? We're going to do some very wild-looking problems over the next 2 days, but it all comes down to basically this. We're going to partition the interval into subintervals, okay? So this interval right now, we're interested in accumulating the area between 0 and 3. Start at 0, stop at 3. How much area is in this shaded portion right here? We're going to do that by breaking it into subintervals. Okay? Now, usually we're going to make equal subintervals. So we're going to make n equal subintervals on the interval from 0 to, on A to B. We're going to do it this way. We're going to find the distance between the two of those, which is going to be b minus a, and then we're going to divide by n. So how far is it from the beginning to the end? Take the right end point, subtract the left end point. That'll tell you how far it is, and then divide by n. That's going to give us what we call delta x, the difference in the x's. Okay? What's our width? Okay? And we call this a regular partition. So we're going to take this and we're going to break it up. Okay, the next thing we're going to do is we're going to make rectangles that approximate the area on each subinterval, just each subinterval, and we're going to use f of x as the height and delta x as the width of each of these rectangular slices. And then we're just going to add up the areas. Just like we did with the area of our hand example, we sliced it up into a bunch of little squares, and then we just added up all the squares to come up with our estimate. Okay? So on a problem like this, here's an easy way to do this. If we're going to go from 0 to 3, let's break it up into 3 subintervals. So I've got an endpoint right here at 1 and right here at 2. So I've got this little subinterval from 0 to 1, little subinterval from 1 to 2, and little subinterval from 2 to 3. Okay, so I've got the width of each one of these, but have I made a rectangle out of each one of these subintervals? No. So then there are lots of different ways that I could go through and I could choose the heights. I could go through and I could eyeball it and I could say, you know what, I think that's a pretty good height right there. And on this one I could say, you know, I think that's a pretty good height right there. And on this one, you know what, I'm going to get a little bit lazy and I'm just going to use whatever this endpoint is right there. Okay, now, if I have the function, could I compute the area of each one of those little rectangles? If I knew how tall each one was. Multiply it by the width is 1. I could come up with an area for those 3 and then just add them together. Would that be an estimate?
Yeah.
It would be. Maybe a good one, maybe a bad one. Maybe an easy one to find, maybe not so easy to find, but that's the idea. On most of the problems that you're going to do, literally we're going to be just slicing up the interval, figuring out how wide each one of the subintervals is, computing a height, and doing base times height, or height times width, whatever you want to think of it as. Okay? So, no matter how you slice it up, there are lots of different ways to choose the height of the rectangle. Yeah, Maddie? Okay, so go ahead and flip the page over. Oh, and I didn't talk about this. Okay, this process of breaking this up and computing areas of rectangles and then adding them up, it is called a Riemann sum. Okay, it looks like that would be a better spelling, Riemann. Okay, don't say Riemann, people will make fun of you. Okay, I believe he was Russian, kind of popularized this idea. Probably wasn't the first one to come up with it, but in honor of him kind of formalizing this, okay, we name these Riemann sums because what we're doing is we're making these rectangular slices and then we're summing them up. So we call that a Riemann sum. Okay, so we're going to do what's called a right Riemann sum, a left Riemann sum, and a midpoint Riemann sum. Okay, so if we're going to do a right Riemann sum, we're going to draw the rectangles using the right endpoint function value as the height. So on each one of these little subintervals, we're going to choose the height in a very systematic way. Okay? So I've got that same regular partition. In this case, delta x is going to be, remember, it's from 0 to 3. So it would be 3 minus 0, and I'm going to do 3 subintervals to make this nice and easy. So each one of these is 1 unit wide. So I've got 0, 1, 2, and 3. And I'm going to blow this up so I've got plenty of space here. Okay, everybody good there? Okay, so I'm going to compute the area on each one of these by figuring out, well, I already know how wide each one of them is, right? Each one of them is 1 unit wide. I want to figure out how tall they are, but I want to do it in this nice systematic way. I want to figure out what the right end function value is. So on this first subinterval, I'm going to go to the right end point of that subinterval, which is 1, and I'm going to compute the value of the function. Remember, the function is x squared or t squared, whatever you want to call it. So this function value right here is 1. And then I just draw a flat top on it and compute that area. Come over here, plug 2 into the function. That's going to be 4. So that's 1, that's 4, and this would be 9.
So is this the right or is this the left Riemann sum? Because on my paper it says left.
Oh, let's see. Are they in a different order on yours?
Yeah. It's left and right and midpoint.
Okay.
But it should still, right should be with the right and left should be with the left.
Yeah.
Okay.
Yeah. Sorry, I apologize. I must have updated this PDF. Okay. So do the right one. Is the right one in the middle for you?
Yeah.
Okay. All right. So do the right one. Good there? Okay. So the way I want you to calculate these is a very specific way, and I want you to do it in this order for a reason. I want to take the height and multiply it by the width. Okay. And in the long run, this will make much more sense. So here's what I get. For this first one, the height is 1 and the width is 1. For the second one, the height is 4 and the width is 1. And on the last one, the height is 9 and the width is, whoops, I'll put it this way so I'm nice and uniform there, and the width is 1. So I end up with, if I add those all together, I end up with 14, right? Any questions there? We're going to get there. Okay. Let's do the left one, wherever that is on your paper. Okay. So for the left one, I'm going to do, again, 0, 1, 2, and 3. On the left one, I use the left endpoint. And on this one, if I plug that into x squared, I get 0 squared. So the height would be 0. Seems a little bit silly, right? For the second subinterval, the left endpoint is 1. So the height would be 1. And on the third one, the left endpoint is 2. So the height would be 4. So again, take the function value, the height, and multiply it by the width. On the second one, it would be 1 times 1. And on the last one, it's going to be 4 times 1. And then I add those up, and what's my left Riemann sum? That's going to be 5. Okay? Okay, now I'm going to make this just a little bit smaller for a second. Here's what the notation that we normally use for these. I'm going to call this an R3. And what that means is that is a right Riemann sum, a right rectangular sum, using 3 equal subintervals. So the answer on that one was 14. R3 represents the right Riemann sum. We're going to do L3 to represent the left Riemann sum using 3 equal subintervals. And then what do you think we're going to, oops, I should write left here. Okay. And this one we're going to do M3. And we always use, for this one, of course, we're going to use the midpoint. Now, if we take a good look at the two of these, I mean, clearly that seems very silly right there to approximate that with a 0, doesn't it?
Yeah.
I mean, clearly there's some area there, so 0 seems a little bit silly. It also seems a little bit silly that on every one of these, we're way over. Okay, and we'll talk more about that in just a second. With a midpoint, if we think about this, let's do this. We've got 0, 1, 2, and 3. When I find the midpoint here is 1/2. The midpoint right here is 3/2, and the midpoint right here is 5/2. So if I come up here and I draw the height right there, now just eyeball that. Doesn't that look like, okay, we're a little over here and we're a little under here, but doesn't it look pretty darn accurate?
Yeah.
Looks pretty good, doesn't it? Same thing happens here. Let's go right in the middle here. Draw that little rectangular height there. That's a little over, that's a little under, but gosh, it looks like it's almost a wash. So if this is going to be more accurate, okay, what do we usually have to suffer through for a more accurate answer? In this case, it's going to be a little more tedious because we're going to have fractions. So again, we're going to take the function height, which is 1/2 squared multiplied by its width. The next one would be 3/2 squared multiplied by its width. The next one would be 5/2 squared multiplied by its width. So on this one, let's see what I end up with. I end up with, this would be 1/4. This is 9/4. Tell me if I make a mistake. And this is 25/4. So altogether, I get 35/4. Or I end up with, if I got a number for that that's a little easier to understand, 8 3/4. 8.75 would be the area. Okay, this approximation that was clearly an over approximation was 14. This one that was clearly an under approximation was 5. So the answer's got to be somewhere between 14 and 5, right? And our midpoint comes up with 8.75. Okay, what would be another way that we could make an estimate to kind of confirm, you know what? The answer is somewhere around 8.75. What could we do with these two to make a more accurate guess? If we know this is an overestimate and we know this is an underestimate, average the two of those. So we add those together, we get 19. Divide that by 2, we get 8.5. No, we get 9.5. 9.5. Okay? So pretty darn close. So the answer is probably somewhere around, if we had to guess, somewhere around 9. Maybe a little more, maybe a little less, but somewhere around there. We've got pretty good evidence so far. And we really haven't done that much work. Everybody good with that? Okay. So let's look at these a little more closely and let's think about some general questions. Okay? And hopefully the yours are in the same order. Which one is an upper sum is the terminology we use for that, or which one is an overestimate? Okay, that's going to be our R3. Which one is a lower sum, or in other words, definitely an underestimate? L3. Now, could we say what the midpoint one is? It'd be kind of tough to tell. You could look at it really closely and maybe take a good guess, but it's really hard to tell unless all of them are clearly an overestimate or all of them are clearly an underestimate. Okay? Is a left sum always a lower sum? no matter what the graph looks like. Nope. Could you think of one where a left sum would be an overestimate?
Just went to the other side of the problem.
Go to the other side of the parabola, okay? Or in other words, if you've got a decreasing function, then every time you choose the left, you're going to have an over approximation, okay? What type of graph would make a left sum an upper sum? It would have to be decreasing. At least on that particular interval, okay? All right, so just some general questions there, and then let's take a look at this. There are other shapes that would be even more accurate than those rectangles. So I could make them like this. I could make the same partition, the same 3 subintervals, and make these shapes. What shapes are those?
Trapezoids.
These are trapezoids. Now, if you take a look at this, I'm going to zoom in on this just a little bit.
Is that the derivative of that one?
We'll get there to how derivatives work and all that sort of stuff. So hold on. Okay. You can look at this right here and you can tell, gosh, there's hardly any error here or any error here. A little bit more right here, but that's really close. What would be the problem with using trapezoids? They're harder to compute. Do you remember the formula for the area of a trapezoid? It does have to do with base 1 and base 2. And there, you can actually do this using trapezoids and you get a very accurate answer. But again, the more accurate, the bigger pain it is to get that, generally speaking. Okay? All right. So we could also do this. Okay? And we'll cover something like this in 5.2. And we'll talk about how this idea applies and how we can make this much more general. I could just go through and just kind of at random break this up into, I'm going to make a really wide width here, a really narrow width here, and then kind of an average one right there. I could break that up. I've got a width for each subinterval. They're not regular widths, but I could do that. I could go through and say, I'm going to draw one here. It looks like roughly a midpoint. This one looks like I chose a height that was closer to the left endpoint. And this one looks like I chose a height that was closer to the right endpoint. So it's just kind of just going through and at random saying, you know what? I'm going to make these widths and I'm going to make these heights. Is this an estimate?
Yep.
It is. Maybe it's better than the ones that we did. Okay? But the bad part about this is there's nothing uniform about it. There's nothing that we could kind of systematize about it. And that's what we're after, is going through this in a very systematic way so we can get this to just crank out an answer that would be exact. Okay? Any questions? Okay, so let's do another one. And let's think about this question right here. No matter how you choose the heights of your rectangles, in a nice systematic way like we did up here with the R3, L3, and M3, right end and right, left, and midpoint, okay, or kind of at random, you could always make it more accurate by taking smaller slices. Okay? So if we did more rectangles, smaller widths, that would be the equivalent of, on our area of hand example, using a smaller grid. It's going to be more work, but it's definitely going to be more accurate. So regardless of how you choose the height, the thinner you make each one of those rectangular slices, the more accurate it's going to be. But if I just did 6 slices rather than 3, I've doubled the number of rectangles that I need to compute and add together. Okay? It would be more accurate, but generally speaking, a bigger pain in the butt. So let's take a look at example number 3. And this is what you typically have on this assignment. It says, find an approximation for the area between y equals sine of x and the x-axis from x equals 0 to x equals pi. Make a regular partition with 4 subintervals. Do a left, right, or midpoint Riemann sum. I don't care which, just pick one. We'll do one together, okay? Or you could choose the height so the rectangles are always an upper sum or a lower sum. So any rectangular height here you want, any way you want to choose them would be just fine. But again, the nice thing about doing a left, right, or a midpoint is it's nice and it's systematic. So let's take a look at what we've got here. Okay, the graph for the sine function looks something like this. And we're going from 0 to pi. So if I'm going to make 4 equal subintervals, the width, delta x, remember the formula is b minus a over n. Well, in this case, b, the right endpoint is pi, the left endpoint is 0, and we're going to do 4 subintervals, so this is going to be pi fourths. So this is going to be, make it look right, this is going to be pi fourths, this is pi halves, this is 3 pi fourths. Okay, now, I would rather keep this relatively easy. Midpoints are more accurate, but they're harder to do. So I'm going to do an R4. 4 equal subintervals, I'm going to choose the right endpoint. And remember, to compute the area, we're going to do the function value times the height. Or we call it a delta x. Function height times the width would be a better way to say it, I suppose. So on this first subinterval, I'm going to go to the right endpoint, and I'm going to compute the height. So this is going to be the sine of pi fourths times pi fourths. There's the height, and here's the width. Okay, on the next one, second subinterval, go to the right endpoint. That's what the rectangle would look like, or at least roughly. Make that look a little bit better. So this is going to be the function value, which is the sine of pi halves, times the height, which is pi fourths. Same one here, right endpoint. So that's going to be the sine of 3 pi fourths. Width is pi fourths. And here's the last one. Silly thing to do on this one, but we do have a couple places where we've overestimated. Okay, so this is going to be plus sine of pi times pi fourths. Every one of these is a height times a width for each one of those 4 rectangles. Any questions? Okay, now to be smart about this, if you're going to do this calculation, notice that every one of these, because we set this up in a uniform way, every one of them has a width of pi fourths. So if I factor that out, all I need to do is compute the sine of pi fourths. So if somebody would be grabbing your calculator, that would be helpful. Whoops. Sine of 3 pi fourths and sine of pi. Now a couple of those you know, this is 1 and this is 0. These are both 1 over radical 2 or radical 2 over 2. So this would be 0, this is 1, this is radical 2 over 2, and this is radical 2 over 2. So R4 would be pi fourths times, let's see, this is going to be 1 plus radical 2. Now, if you type that into the calculator, what does it say? 1.896. Okay, approximately. Everybody okay with that? Okay, how could I make this more accurate? Using the exact same method. Smaller sections. So that's what I want you to do on this one. We want to express the area in example 3 using 8 equal subintervals and right endpoints. So if I did 8 equal subintervals, let's be smart about this. This is going to be pi minus 0 divided by 8. So that means delta x is pi eighths. So that means I'm going to go here, 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 and here. I have 8 subintervals. So this is going to be pi eighths, pi fourths. Or I think you'd be better off writing 2 pi eighths, just so you could keep track of it. 3 pi eighths, 4 pi eighths, 5 pi eighths, 6 pi eighths, 7 pi eighths, and that would be 8 pi eighths right there. Okay, watch please. If I did this first one, it's going to be the sine of pi eighths times pi eighths, right? Second one is going to be the sine of 2 pi 8s, okay, times pi 8s. Every one of them is going to look like that. They're all going to have a pi 8. So let's be smart about this. Let's write the pi 8s out front, and then we can go through and look how systemized this is. What's that? Oh, R8. Yes, thank you. Thank you. Yep. So this is going to be the sine of pi 8s plus the sine of 2 pi 8s plus the sine of 3 pi 8s. And then I don't even have to think about what the graph looks like. I just keep going. Now, you do have to keep track of this. This would be 4 pi 8s, 5 pi 8s, 6 pi 8s, 7 pi 8s, and let's see, when do I stop? Okay, 8 pi 8s. Okay, let me make this just a little bit smaller so you can see this. How many subintervals did we have? 8. Okay, this started off with a 1 pi 8s, so that little number right there is like your counter. If I have 8 rectangles, I better have 8, these are heights, right? I better have 8 heights. Please don't go through, and I almost guarantee somebody's going to do this on the test. They're going to go through, and because of the way the data is going to be given to you or something like that, they're going to put 9 of them here, they're going to put 7. Make sure you have, if it's 8, get 8 of them, okay? What if I went through and I did left endpoints? This is how cool this systemizing method is. If I did left endpoints, what's the first one? It would be 0. So guess what I'd put right here? 0 pi 8s. What would I put right here? 1, 2, 3, 4, 5, 6. Stop right here at 7. Why do I get to stop at 7? Because that's 8 of them. I started at 0. I started at the left endpoint. And 7 pi 8 is the left endpoint of the 8th subinterval. Does that make sense? Okay. Any questions? Okay. We've got a couple minutes left. This is what I'd like to do. I'd like to brush on this right here. Juan actually alluded to this. We're going to be using sigma notation, the stuff that you learned in Math 1050, in order to make this so we can actually get an exact answer for this. Not approximate it. Get an exact answer. Not guess what it is, know for sure what it is, okay? But you have some problems that are very similar to this. And we're going to be talking about some very complex ideas today and tomorrow. The problems are very, very simple for the most part, okay? So don't get overwhelmed with the idea and not be able to do a simple problem. Literally, you're breaking up an interval into subintervals. You're figuring out how wide each subinterval is and computing a height and then calculating an area for each one of those and adding them up. That's it. If you can do the width times the height to get an area for multiple rectangles and add them up, that's it. Okay? And that's what we've got here. Okay? So on this problem, this isn't about distance. Okay? It says, suppose a car starts from rest and accelerates according to the following table. So this is acceleration. So this is the acceleration in feet per second squared. And this is the time in seconds. So don't look at the data yet. Let's say I did this. Let's say I drew a rectangle on there. How tall is that rectangle? 4 feet per second squared, right?
Yeah.
How wide is it? 1 second. What would 4 feet per second squared times 1 second be? 4 feet per second. Okay? So that area wouldn't represent a distance, it would represent a velocity. I got acceleration graph, I can figure out velocity. I've got a velocity graph, I can figure out position. Okay? Think about that. That's a very powerful idea. So when I mark down this data, this is an acceleration graph, which means the areas underneath that are going to be velocities, okay, because of the way the units work out. Now, if you have a piece of data like this, notice that we don't skip anything. It just goes from 0 to 1 to 2, 3, 4, 5, okay? Here's what I would do. When you put the data on there, I would mark what the value is. It's a lot easier to tell, you know, when you come back to look at it. At 1, it's 5. At 2, it's 8. At 3, it's 9. At 4, it's 8. And at 5, it's 4. Now, we've done right endpoints several times. Do you want to stick with right endpoints? They're relatively easy. We probably would not do midpoints on this. Why would we not do midpoints here? It doesn't give us that. We don't want to make up data. Okay? It doesn't give us the values. So really, either a left or a right would be fine here. I'm going to do a left on this one. So left endpoint, 0 for a height. Left endpoint, 5 for a height. Left endpoint, 8 for a height. Left endpoint, 9 for a height. And left endpoint, 8 for a height. There are the 5. Let's make this easy. How wide are every one of them? What's the width for each one? 1 second. What's the first value? 0. Feet per second squared. Next one? 5 feet per second squared. Next one is 8. And again, I'm kind of belaboring the point here, writing down every one of those. And then the last one is 8. Okay, now, do I have enough in here? How many heights do I have?
5.
I've got all 5 of them. So this is going to be 1 second times, let's see, add those up. Is that 30? It's 30, isn't it?
Yeah.
30 feet per second squared. Cancel that with that, and I end up with, how fast is it going at the end? 30 feet per second. So we can find, and if I were to connect this, I don't have the data for this, but this would probably be a good guess for what the acceleration curve looked like. The area underneath that curve, the area underneath the acceleration curve has accumulated a velocity change of 30 feet per second. So if it started at rest, how fast was it going after 5 seconds? 30 feet per second. What if it started out at, say, 10 feet per second and still underwent the same velocity change, the same acceleration? We'd add those together and we'd get 40. Okay? Any questions? Okay. I'm going to pick up right here, but we are going to talk about sigma notation tomorrow. It would be really nice if you could look over this page. If you haven't seen sigma notation for a long time and it's like, holy crap, what is that? I would suggest you either do some searching on the internet, pull out your notes from 1050 or something like that and go over those. Okay, because we're going to rely on that a fair amount. But you have enough tools right now that you could do almost the entire assignment, because all you have to do is take the information, think about the graph and how many subintervals they want you to do, compute a height, multiply it by a width, compute a height, multiply it by a width. Even if you have to do that 8 times on one problem, it's a relatively simple thing to do, okay? Please get started on the assignment and look at sigma notation so we can pick up there tomorrow, okay? Thanks.